Okay, in this video, we're going to go through the review exercises at the end of chapter 11, which talked about the R.M.S. error for regression. Okay, so yeah, but these review exercises at the end of the chapters can contain material from previous chapters. It's kind of comprehensive. The R.M.S. error of the regression line for predicting y from x is what? The R.M.S. error for predicting y from x, you do the square root of 1 minus r squared times the standard deviation of y, the output variable, right? So that's this. A computer program is developed to predict the GPA of college freshmen from their high school GPAs. This program is tried out on a class whose college GPAs are known. The R.M.S. error is 3.12. Is anything wrong? Answer yes or no and explain. Okay, so yeah, so we're predicting GPAs of college freshmen from the high school GPAs. The R.M.S. is 3.12. I would say yes, something's wrong, because it would be like if you, the whole idea is if you had a high school GPA of a certain student was 3.2, right? And so you're saying, okay, I want to predict the college freshman GPA of that student, so I'm going to use regression and I'm going to get something like, 3.4, right? That's my prediction. So what is the R.M.S. error saying? It's saying, okay, with what certainty do I know this GPA? How look, I'm saying it's 3.4, but I'm going to be off by plus or minus, we would expect something like 0.5 or 1 maybe, or something like that. But plus or minus 3.12, that's too much. So yeah, something's wrong. Tudenham and Snyder obtained the following results for 66 California boys at ages 6 and 18. The scatter diagram is football shaped. Okay, so we know it's football shaped. Okay, and we've got this data, average height at 6, average height at 18 for these 66 California boys. So find the R.M.S. error for the regression prediction of height at 18 from height at 6. Okay, so that's just going to be, this doesn't even matter if it's football shaped or not. So 1 minus 0.8 squared times, and now the standard deviation in the variable we're trying to predict. So for the prediction of height at 18 from height at 6, so height at 18, that's 2.5. 1 minus 0.8 squared times, so 1.5. Okay. Find the R.M.S. error for the regression prediction of height at 6 from height at 18. So this is just going to be, we're doing this times 1.7. So 1.02. It's just the opposite. Now we're doing, we just, the output variable was the height at 6. So we use that standard deviation. Okay, a statistical analysis was made of the midterm and final scores in a large course with the following results. So here's the averages and standard deviations, correlation coefficient. The scatter diagram was football shaped. For each student, the final score was predicted from the midterm score using the regression line. Okay. Let me bring in the question. Okay. For about 1/3 of the students, the prediction for the final score was off by more than, okay, what they're talking about here is, what they mean by 1/3 is, if we calculate, it's football shaped, so if we calculate the R.M.S. error, we'll get a value, right? So let's do that. So square root of 1 minus 0.6 squared times, and then we're predicting what? Final score was predicted from so we're predicting the final score. So times 15. Okay, so 12. The answer is going to be 12 here. And what they're talking about is the fact that, so if it's football shaped, it's normally distributed, the data. And so you kind of look at that as standard deviations. It's like if you're one R.M.S. away from the regression line, then it's like with the normal distribution, that's you're kind of like one standard deviation away. You're only 33% are within one standard deviation. It's that whole idea It's kind of how you view RMS. It's like standard deviation with respect to the regression line, if the data is football shaped. Okay, predict the final score for a student whose midterm score was 80. Okay, so with a midterm score of, this is just regression, so midterm score of 80, we've got 30, we're 30 points above average, so now divided by 25, it's that many standard deviations in the x direction. So now we apply that same many standard deviations in the output, but now times 0.6. So now the final score, we add that to 55, so 65.8. Okay, the prediction is likely to be off by the R.M.S. Right, it's football shaped. Okay. Use the data in exercise 4 to answer the following questions. Okay. About what percentage of students scored over 80 on the final? So let me bring this back again. So about what percentage of students scored over 80 on the final? All right, so it's football shaped, normally distributed. So we'll do over 80 was, we just used, just focus here on the output variable and treat it like it's normally distributed. So this is 80 minus 55 is 25. So 25 divided by 15 is that. So that's the z-score. And so now we use this formula here for the normal distribution. This is in percent. You could do it however you want. And so we're going to go from scored 80. What percentage scored over 80? So we're integrating from this z-score to infinity. 4.8%. Okay, of the students who scored 80 on the midterm, about what percentage scored over 80 on the final? All right, well, that's going to be, we use regression. So did we answer that already as far as predict the final score for a student whose midterm score was 80? Okay, yeah. The average here is 65.8, right? If we use regression, that's what we did here. So now we've got this new average. What's the new standard deviation? It's the 12, the R.M.S. So now we say, okay, what percentage scored over 80 on the final? So this is what we did in the last section. We're treating the strips like they're normally distributed. So 80 minus 65.8 divided by 12. There's the z-score. So we do this to infinity okay, 11.8%. All right. Okay, in a study of high school students, a positive correlation was found between hours spent per week doing homework and scores on standardized achievement tests. The investigators concluded that doing homework helps prepare students for these tests. Does the conclusion follow from the data? Answer yes or no and explain briefly. So to me, there's not enough information given here. What information do we not have? They don't tell us what the correlation coefficient is. They tell us it's positive, but they don't give us a value. But then, really more importantly, they don't tell us if it's football shaped or not, the data. If they told us that it was football shaped, but they didn't tell us the value of the coefficient, well, then we have to think about, okay, well, what if R was like 0.1? If it was 0.9, then we could say for sure that, yeah, this conclusion does follow. But, you know, if you think about it, even if the correlation coefficient is 0.1, assuming that there's a lot of data points, or sufficient amount, right? For any statistical case, if there's not enough data points, then you kind of, it's not appropriate to make conclusions to a certain extent. But okay, if it was like 0.1, right? Just sloping up very slightly, something like that, right? You can still, to me, you can make this argument. it kind of gets a little bit sketchy to make the argument that if it's really loosely correlated, but you could make the argument, right? In general, if you compared a vertical strip here to a vertical strip here, then it is true. It's to some extent, it seems to be the case that because there's a positive correlation with a football-shaped scatter plot, it seems to be the case that doing homework helps prepare students for these tests, okay? But they don't tell us that it's football-shaped. So what does that mean? Well, that means we can have something nonlinear. In that case, the linear correlation coefficient doesn't apply. You could have something like, like a quadratic that's sloped upwards. So the correlation coefficient is going to tell you positive, but that's not, that wouldn't be the case here, right? It looks like if you spend too many hours studying, it has a negative effect. So you couldn't make this general statement that overall that wouldn't be appropriate to make a general statement that doing homework helps prepare students for these tests. You have to be more specific. The freshmen at a large university are required to take a battery of aptitude tests. Students who score high on the mathematics test also tend to score high on the physics test. On both tests, the average score is 60. The standard deviations are the same too. The scatter diagram is football-shaped. Of the students who scored about 75 on the mathematics test, we want to choose an option here. Just about half scored over 75 on the physics test, or more than half scored over 75 on the physics test, or less than half scored over 75 on the physics test. So, okay, we want to think about here how, so we know the diagram is football-shaped, and that's important. And they've kind of implied that there's a positive correlation here, because it's saying students who scored high on the mathematics test also tended to score high on the physics test. So we've got some football-shaped diagram that's slanted upward to some extent, right? Now, the average on both tests is 60, okay? Now, we can add in a regression line here. So the standard deviation line would be something like this, right? And so we know that the regression line in general, unless it's a perfect correlation, is going to be shallower than the SD line. So, okay, something like that. Now, what we've got then is we're looking at the scores of 75 on the mathematics test, right around 75. And the question is, for the students that scored 75 on the mathematics test, what percentage of those scored better than 75 on the mathematics test or no, on the physics test? So, all right, we have to really think about this because, okay, we've got all these data points in here, right? Now, if we think about the regression line, this is not going to be a 75, right? This is going to be the SD line corresponds to 75. It's the same standard deviation and average for both data sets. So it's going to be on the SD line where we would get a 75 on the math and physics test. But we're on the regression line, we're below 75. This is like something like 69. Okay, so now, but what does that mean? Well, when we think about a football-shaped diagram, we know that the idea is there's like an even distribution of data points around the regression line. You might say, well, so like there's like the same number of data points on above and below the regression line. You might say, well, no, that's just the average. You might have more data points, or you might have less data points above, but they're more spread out. And so that pulls the average up. Well, no, not if we're assuming an ideal football shape, right? For like the ideal football shape, it's like normally distributed in about the average. So we're going to have about 69. We're going to have, the idea is for the students that scored 75 on the math test, just about half of those scored over 69 on the physics test. That's why with football shapes, your percentile tends to go down a little bit if you came on the input variable with an above average percentile. On average, your percentile is going to go down a little bit. So in that case, if this is where 75, the score of 75 is, then less than half scored 75 on the physics test. Okay, the bends are caused by rapid changes in air pressure, resulting in the formation of nitrogen bubbles in the blood. The symptoms are acute pain and sometimes paralysis leading to death. In World War II, pilots got the beads during certain battle maneuvers. It was feasible to simulate these conditions in a pressure chamber. As a result, pilot trainees were tested under these conditions once at the beginning of their training. If they got the bends, only mild cases were induced. They were excluded from the training on the grounds that they were more likely to get the bends under battle conditions. This procedure was severely criticized by the statistician Joe Bergson, and he persuaded the Air Force to replicate the test, that is, repeat it several times for each trainee. Why might Bergson have suggested this? Give another example where replication is helpful. So, I mean, maybe the pilots could kind of build up an immunity to it. It's kind of like endurance, right? You know, you do it for the very first time, but if you kind of stick with it a little bit, you gain strength, develop an immunity to it. Yeah, so he must have been. So if we look here, we're assuming they did a lot. There's enough data points, but he must be thinking. Well, obviously, he is thinking from some perspective that there's a confounding variable at play. So pilot trainees were tested under these conditions once. So these are pilot trainees. So they have minimal experience flying. And so maybe Joe Bergson is just thinking, you're not doing the test right. You have to ease them into it, let's say. You got to get them in the air and kind of get them used to the conditions and then do the test. I mean, I don't know. I don't know about pilot training. He's obviously thinking that there are confounding variables at play. And so maybe if you test the pilots more than once, you might see, okay, all of a sudden they're not susceptible to it. There's only certain people that, so, okay, let's think about like seasickness, for example. Well, if you have some kids that have never been in a boat and then you just put them out in a boat one time and they get kind of seasick and you say, okay, you're not going to be going in a boat anymore. Someone might say, well, no, I remember thinking to themselves, I remember getting kind of seasick when I first started, but when I went out the second or third time, I never got seasick again. Whereas other people, it might be inherent, no matter how many times they go out in the boat, they're always going to get seasick. So, okay. Every year, baseball's major leagues honor their outstanding first-year players with the title Rookie of the Year. The overall batting average for the Rookies of the Year is around 290, far above the major league batting average of 260. However, Rookies of the Year don't do so well in their second year. Their overall second season batting average is only 275. Baseball writers call this the sophomore slump, the idea being that star players get distracted by outside activities like product endorsements and television appearances. Do the data support the idea of the sophomore slump? Answer yes or no and explain briefly. Well, to me, the textbook is obviously wanting us to say no. Because this is the classic example of what they have cited as a regression fallacy. And I'm saying the textbook wants us to say this. I'm just saying that because, look, if you need to be a professional baseball coach, manager to really give the best answer to something like this. But what they're saying here, if we come back, here are the key words, okay? The overall batting average of the Rookie of the Year is around 290, far above the Major League batting average of 260, right? This is one of the key statements. And why this is a key statement is because you're bound to, on average, you're gonna if you did this well to start, you had such a great rookie year, well, you're gonna come back a little bit on average. You're already far above the regular average, the entire league average. So what they're saying is that attributing this to some sort of reason, they've gotten distracted by outside activities. I mean, you don't even need to be a professional in baseball to say this is the regression fallacy. That does seem kind of silly if you would say this, because you're already well above the league batting average. You had a great year, and the second season you're batting 275. That's still greater than 260. The average, you're still doing well. So, yeah, this is the regression effect. Okay, a study was made of the relationship between stock prices on the last trading day of 2005 and the last trading day of 2006. A formula was developed to predict the 2006 price from the 2005 price using data on 100 stocks. An analyst is now reviewing the results. Data are shown below for 5 out of the 100 stocks. Prices are in dollars. Was the regression method used to predict the 2006 price from the 2005 price? Answer yes or no and explain. If you need more information, explain why. Okay, so how can we try and unpack this to see, was the regression method used to predict, to make these predictions? Well, the one thing we can check just to start is the 2005 price, which is the input, and the predicted prices, do those all fall on a line? If that's not the case, then no, the regression method wasn't used. If they do all fall on a line, then we'll have to go from there. So let's see. You've got the 2005, 2006. So 10-8, 10-8. Then you go, I don't need this table. Then you go up 2 in the input, then up 3 in the output. So rise over run is 3 halves, right? So then we go up 2. From there, we go up 2 in the input and down 1. Then we go up 1 and up 8. No. So no. Remember, this is predicted. Yeah, actual, we wouldn't expect to necessarily fall on a line. That's like the point of averages. Or no, I'm sorry, that's not right. Actual is not the point of averages. That's just the points of averages are what we would ideally want to predict, but actual is just random, right? That's based on what the R.M.S. It should be like around the R.M.S. We expect the actual to be most of the time to be within the R.M.S. But the predicted is the regression line. That's what we predict, and it's a line, right? So no. The figure below is a scatter plot of income against education for a representative sample of men aged 25 to 29 in Texas. Or is something wrong? So what? The figure is a scatter plot of income against education for a representative sample of men aged 25 to 29 in Texas. Or is something wrong? What does it mean, or if is something wrong? So that means it's not really this plot. This can't. They're saying it can't be the case that this is a plot of income level of men aged 25 to 29 in Texas. So in that case, yeah, I guess something is wrong. How could you have an educational level, these data points? Let's see. Oh no. That's not. We should be okay there. Years of schooling completed, not including kindergarten. So first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. So 12 years of schooling. Then if you're 29 years old, you've got potentially another 10 years of schooling, 11 years of schooling. So in that 22 range, yeah, that's right. Okay. And then you could have, well, no. How could you have data points down here if the ages are only 25 to 29? You would expect the educational level then to be, so you have 12 years of schooling, you're 18. Then if you're 29 years old and you stayed in school, went to med school or whatever, then that means you could have like 22 years of schooling, 23 years. So, okay, we're good there. But then we go to, let's see, 23, 22, 21, 20, 19. We would expect, so how could we have data points below this? Right? How could somebody have 8 years of schooling only and be within the age of 25 to 29? Is that possible? It can't be possible. Oh, well, no. I guess you could. Yeah, like you dropped out or something. Yeah, okay. Yeah. Okay. So that's possible. If you're a high school dropout, but then you dropped out in 10th grade, but now so you were how old? You were 16 years old, but now it's 10 years later and you're in the study. So, okay. And that could be the case even if you only have like 1 year of schooling you dropped out after first grade. Do people do that? But then you dropped out after first grade, but now they're saying what's your income level 15 years later or whatnot. So I guess these would be some pretty poor people. I don't mean to laugh at that. Or maybe just the circumstances dictate that it's hard for them to even stay in school for some reason. But okay, you've got a low income level here, and then the income rises with educational level. That makes sense. I mean, it's heteroscedastic. It's not football shaped, but there's nothing wrong with that. Heteroscedasticity doesn't mean something's wrong necessarily, because you just have with a higher education level, there's just more job options. There's different things you can do. There's just different circumstances. Some people become CEOs, some people don't, and that's exactly why it is. Whereas at a lower education level, it's these kind of cookie cutter type jobs and promotions and whatnot. So no, this seems normal. Nothing is wrong. Okay, for the men aged 25 to 34 in Haynes 5, the relationship between education, years of schooling completed, and systolic blood pressure can be summarized as follows. Okay, one man in the sample had 20 years of education and his blood pressure was 118 millimeters. True or false and explain. Compared to other men at his educational level, his blood pressure was a bit on the high side. Okay, so did it tell us that this was football shaped? No, but I mean, we can assume that's what they're wanting us to do. So, all right. So let's think about how 20 years of education is the input. Okay, so what's the average for the regression line? So 7 years above average divided by 3. Okay, now we want to go the same number of standard deviations with respect to the output, but then multiply that by the correlation coefficient. So we're going to go this much below average with respect to blood pressure. So there's the new average, 116 millimeters. The new standard deviation for this is the R.M.S, right? Assuming it's football shape. So 0.1 squared, 1 minus that. Okay, now times the standard deviation in the output. So 10.9. Okay. Now, the question is, compared to other men at his educational level, is it true that his blood pressure was a bit on the high side? This person who had 20 years of education and his blood pressure was 118. So this is false. His blood pressure was a bit on the low side. He was below average. Or no, wait. No. The average was 116. He was 118. He was a little bit above average. So true.